Okay, so we continue from the second part of the lithography. So the first part is the sort of the example, the introduction example, and then we continue this from the previous class. So let's imagine the two situations of the stamp. So you make a stamp. So the one stamp is, say, as typically that I draw in the previous class, where versus you have say looks like simple. So you can maybe imagine that well, if I can make this, maybe I can make this. Maybe you can think like this way. But actually, in practice, it's difficult. It's totally different because, say, from here to here, this is a height. Right? This is a height. Say height 1, and this one is, say, height 2. So what determines height 1 and 2? Well, in which process? In which process? Control. Which process control height 1 versus height 2? This is questions, right? So if you recall all the process, and then you have, say, you put the mask, and then illuminate light, and remove this photoresist, the polymer. The polymer is called, a different word is photoresist. So remove the photoresist, and then you got a patterns, and then you pour the rubber-like solution and curing to make a solution to solve it. You make this. So eventually, your initial the photoresist, which is the polymer solution, photoresist thickness determines H1, H2, because you have, say, to make this, for example, I can draw, and you have a surfaces of silicon wafer, then you have the spin-coated photoresist of this thickness, which is corresponding to H1. And then you've got a mask, and then you illuminate and remove these patterns and pour the silicons and stamp materials. But if you make this one, your photoresist solutions, the thickness should be like H2, right? And then you got a mask, and then you illuminate light and remove this photoresist, and then do whatever the subsequent process that we mentioned in a previous class. So as you know that, as you expected, that if a photoresist can make this thickness H1, so question is, can make this H2? Well, the answer is yes or no. Because if you think about honey, for example, the honey solution, which is very sticky, if you have very, very thick honey solution, and then you've got to rotate, drop the surfaces of the honey, and then you rotate and make a flat layers of honey. If there is very thick viscose, and then you make this, end up with this thickness. But if the situation is the honey mixed with water, 9-to-1, for example, 9 is water and 1 is honey, then it looks like a little bit viscous, but it's similar to water. And then you gotta pour the surfaces and you rotate it, make this, right? So the vice versa. But can you make this low viscous solution make this? No. The answer is no. Can this very viscous solution make this? Actually, the answer is no, because it's very viscous. Even if you're very, very fast rotating, but still they have a certain limit exist. that certain below a critical thickness cannot go below even thinner, cannot do it. So that's why you know this how to make this, doesn't guarantee to make how to make this, doesn't guarantee anything. Right? So these all the things are all depending on, it's truly depending on upon this type of the photoresist. Which is polymer solution, type of the photoresist. Okay. So there are two types of photoresist. So one is positive photoresist, and there's a negative photoresist. Okay. So the definition of the positive here is this is practical definition because it's the whole practical process of the lithography. So the practical definition is, so the positive means the polymer exposed by light, right? It's got a flat surfaces, flat layers of the polymer. The part that illuminated by the light is removed. Right? It makes sense, right? So that part say, so this is my hand and this polymer layers, and I got this my nail and this part they got illuminated and removed. They positively behave. Right? This makes sense. So the opposite concept is a negative photoresist. That means the polymer exposed by the light is remained. Right? It makes sense. It behave opposite way. So the question is then what type of a polymer is it? What type of polymer? So what type of polymer that make a positive behavior? So what type of polymer can negative behavior? So if I ask you about this, say degradation, as in the previous class I gave you, there are two different behavior of sensitivity, responsiveness of the polymer solution upon the light illuminations. One is degradation, one is the other further polymerization start from the small molecule and polymerize. Degradation or polymerization. The question is very simple. So the positive is actually degradation because you gotta light illuminate it and then degrade it and then you can remove by the solvent. So negative is actually the light is polymerized and then remained because the molecular weight is increased. Right? So this makes sense, right? So then then you can actually see this high aspect ratio is high aspect the morphology that actually made by the negative, usually negative photoresist. And this is a positive photoresist. So that makes a totally different photoresist you have to use it. So there's more details and what is a photoresist, how it structures a photoresist, and you have the detail study yourself. But this class is basically give you a rough idea that how we use it, this properties and what its applications are. So there's a totally different situations. Using one is positive photoresist and the other is negative photoresist. So that makes different cases. Okay. So in a differently. If I have you have a soft lithography, but it's a photon you use it, but it can be an electron, or it can be X-ray, whatever light source you have. Say if you have an electron, soft electron lithography, it means that you have everything same, but you have say the light source is electrons. For example, you have say the polymer layers. In this case, this is E-beam. This is the electron beam. So E-beam photoresist we call it. If you say just regular photoresist, then this is light photoresist, responsive to the UV light. But it's E-beam photoresist. So the E-beam wavelength is much shorter. That means short wave length means high resolution. High resolution means a smaller object you can make. So that is the advantage of this E-beam resist. So anyway, so this E-beam photoresist, which is a polymetal methacrylate, which is there's some representative E-beam resist to use it use it outside. So that is E-beam is PMMA. PMMA is got an E-beam exposed. The E-beam is exposed in here. Then they are gone. So this is the E-beam photoresist. Do you need a mask? In the E-beam lithography? The answer is yes or no. But generally, no, we don't need it. So this one big difference is generally speaking, one big difference between photo lithography versus E-beam lithography is the use of mask. So this is no mask, then if there is required mask, always. The photoresist case is always yes. They have to use some photo mask. So we don't need the photo mask, E-beam photo mask in the case. Actually, you see, it's very simple reason. So you see SEM or the imaging tool that we know everything. So I mean, it's the scanning electron microscopy or TEM, transmission electron microscopy. This is electron, right? So electron, then you see your object of the micro features and nano features object. You put in the SEM or TEM, especially in SEM. Then they show you the morphology of microstructure and nanostructures. So you got for example, you got a hair. You put the SEM machine. They got surface of the morphology of your hair. You can see micro layer by layers of structures and fine structures, right? How do you do it? The electron actually can scan. It's very rapid, right? Very rapid. So you got an electron gone. You got an object and it's very fast. You can scan. So that's what is all time. Got a TV, right? TV is basically electron beam, right? And electron gone behind it. The brown gun TV that is a long time, 10 or 20 years ago. The old time TV that is very thick. Now it's very thin, which is a OLED, but there's now a thin. There's electron guns looks like this. 3 electron guns, and there's a individual light they actually scan. So that's why their scan rate is very fast, very fast. And then they can actually see which area they can shoot the electron, which area doesn't shoot the electron. So they can actually control in the brown gun you have this beam can go here, can skip this part and goes here, skip this part and goes here. So you can actually electronically very sensitively control all the positions that you can do or do not of this electron. So that's why you have you got a line of this. Put the electrons here in a very fast way. You can actually control no, yes, you can do it. So that's why generally speaking, the electron lithography, we don't need the mask. Photon, for example, the light you cannot control, right? I mean, you cannot tell this light illuminating this part, not illuminating this part. So you cannot control. That's why you have a mask. But electrons you can control. So that is a big difference. This seems like then you have a high resolution, short wavelength E-beam, high resolution, no mask, so it seems to be much better than photoresist, right? So everyone can use electron microscopy, electron beam lithography. No, the answer is no. There's a big disadvantage compared to photolithography. Is that there's a throughput, the speed. Speed or throughput. So similar concept. Speed or throughput means the electron beam, they scan actually. From this pattern here, you can any way you have to scan, illuminating this electron beam here or not, yes, no, anyway you have to one by one line-based process, you have to do it. But you think of the photon is very fast because photon is you illuminate using the mask, you got a one shot. Wow. The electron actually they scan. So actually the photon is much faster. So that's why the semiconductor industry that has a very high throughput, many different same circuit, and then they don't use the electron beam lithography. They actually use the photoresist. That's why this reason. So this commercial our usual semiconductor is based on the photoresist. But in school like this, or some special purposes, actually they use the E-beam photoresist because they custom made. Custom made, you need this shape, this thickness, can do it, but you don't have the mask for appropriate mask. Then actually you use a E-beam lithography to make, or one or two that for your purposes. Then you use this technique. Right. It's not a throughput. It's not a fast. So that is one disadvantage. So the process is usually when you make the photo mask, this mask that used for photolithography, this mask usually made by the E-beam lithography because you can make a custom way to make this mask, and then you go to the photolithography, use this mask to make large scales or fast scales of the lithography. So there is one big difference between E-beam or photolithography. So saying, why we need this technique then, as I introduced in the first lithography part 1, then you can do a lot of different things. Say, for example, if you can make this surface, for example, and then you want to have this line, say, you got 3 lines of it. So the underneath is a glass and transparent. So you can make a protein and collagens, you can make it. Using this soft lithography technique. And then you put the cell. Then put the cells, and cell goes to growing this part. So I draw again, for example. Then cells recognizing protein. Remember if you forget, then go back to the mammalian cell culture part. Cells recognizing protein, they grow there like this. Like this, not going this way. Or if you can do different things, or you can do like this patterns, then you can cross 2 different cells, for example. Then you can study the communication between one type of the cell, second type of the cell with this junction point. You can do a lot of different things how you design experiment. If you know this technique, then you can design experiment. You can do a lot of different things. Cell type number 1 or 2, or it can be neuron cells, can go dendrite from here to here directly. What is the responsiveness if there's no proteins? What is the dendrite Does the dendrite actually grow through this empty space or does not grow the empty space, for example? A lot of different things. Also, if you have very high aspect ratios of the stamp, you make it in the previous, go back to the part 1 of the lithography class, and this grow the cell, and instead actually contract this like this rubber, because the stamp is rubber, so they can actually flexible, so it can actually contract this, applying the force out of the pillar. I can call this pillars, or pillars actually bend it, so you can calculate, if you know the spring constant of this pillar, so spring constant force is kx. If you know the spring constant of this pillar, then you can actually calculate the force that this cell can apply this system. So you can do a lot of different things, or you can make a sensor out of it. So you can make these cells, and then you flow some useful component, for example. Component in these cells can actually be responsive in one time and is not responsive for this type of the cell, is medium responsive to this type of cell. You can make a sensors and have those drug responsiveness. You can do a lot of different things. So this soft lithography, generally speaking, that is a technique coming actually from the semiconductor industry, but actually useful for studying the biological system in the chemical biology system. So if you can read this, say, soft lithography review paper by, say, George Whiteside, for example, Professor George Whiteside, and other people, there's the pioneer of this soft lithography. You can cross Google this name and this key word, and you can find very useful paper, scientific papers. You can have more informations. Okay. Okay. So this is the part of the lithography, the end of the lithography part, and then we continue the next topic in different class. Thank you very much.